In any bounded container, billions of gas molecules move at vastly different, constantly changing speeds. This continuous sequence of collisions makes individual tracking mathematically impossible. Yet macroscopic properties like temperature and pressure are derived from the velocities of these invisible, microscopic components. Statistical mechanics provides the mathematical framework necessary to solve this tracking problem. In the 19th century, physicist James Clerk Maxwell developed a foundational mathematical relation to predict this gas behavior. Rather than attempting to follow a single particle, Maxwell used a probability density function to calculate the likelihood of molecules operating at specific speeds across the system. By mapping the geometry of this relation, we visualize exactly how thermal energy manipulates molecular chaos. Understanding the whole system required physicists to move past the individual particle and calculate the statistical average. This is the mathematical relation Maxwell proposed for the distribution of molecular speeds. The term n sub v is the Maxwell-Boltzmann speed distribution function. On the right side, we find the physical variables, mass, m, temperature, T, and total number of molecules, N. This algebraic expression draws a specific geometric shape when plotted on a graph. We define the horizontal x-axis as the molecular speed, v. The vertical y-axis represents the relative number of molecules operating at a given speed. The function produces an asymmetrical bell-like curve rising from the origin. Dropping a line from the highest point of the curve to the x-axis identifies a specific velocity. This intercept is v sub mp, the most probable speed of a molecule in the system. This resulting curve provides a perfect mathematical snapshot of chaotic gas speeds at a single moment in time. To extract macroscopic data from this continuous curve, we rely on the principles of calculus. We isolate a range of speeds by taking a differential slice under the curve. Its horizontal width is dv, representing a tiny speed increment. The vertical height, from axis to curve, is the function value n sub v. Multiplying the height by the width gives us the area of the slice, which we call dn. Physicists interpret dn as the precise number of molecules possessing a speed strictly between v and v plus dv. To find the total number of molecules in the container, we must calculate the area for the entire system. Integration allows us to find this total by summing up an infinite number of these vertical slices, from 0 to infinity. The mathematical integration of the function n sub v with respect to v equals n. The total geometric area under this statistical curve represents the physical count of molecules within the gas. Analyzing the geometry of this curve reveals an asymmetrical profile rather than a standard parabola. A long tail extends right. Speeds stretch toward infinity, but cannot drop below 0. The most probable speed line splits the graph. Area 1 represents molecules moving slower than this speed, and Area 2 represents those moving faster. The area of A2 is strictly greater than the area of A1. Because geometric area correlates to particle count, this inequality has a specific physical consequence. The visibly larger area on the right directly indicates a much higher count of molecules moving at high velocities. In any gas system, the number of molecules moving faster than the most probable speed will always exceed the number moving slower. Temperature is the dynamic variable that alters the shape of the distribution. We begin with a baseline curve, labeled T1, for a gas at an initial cooler temperature. We must consider what happens to this probability curve when heat energy raises the temperature to T2. The peak of the distribution curve shifts to the right along the x-axis. This shift indicates that the most probable and average speeds of the molecules have increased. The curve also broadens horizontally. Higher temperatures increase the variance of molecular speeds, spreading the particles across a wider range of kinetic states. Even as the shape changes, the total area under the curve must remain equal to n, the total number of molecules. To maintain a constant area while the base stretches wider, the vertical height of the peak must drop. Adding thermal energy flattens and stretches the statistical distribution, shifting the system into a wider kinetic profile. Maxwell's law bridges the gap between individual molecular behavior and the observable world. The chaos of billions of individual particle collisions is resolved into a predictable distribution formula. Calculus allows us to translate the area under a probability curve into a physical molecule count. Mapping the asymmetry of the curve reveals a persistent natural bias toward higher kinetic energies. Temperature physically warps the shape of that probability while strictly obeying the boundaries of total mass. This demonstrates the overarching power of statistical mechanics. The predictable laws of thermodynamics are built upon a foundation of microscopic randomness. Maxwell's work proves that by calculating the distribution of chaos, we gain the ability to predict the behavior of the universe.